All right, there we go. No one else, but I'm supposed to be recording my lecture. All right, cool. Great. Okay, so the surface of the star is initially at what we'll call chi 0, chi naught. Just chi naught. Okay. I can even use this part now. And so the surface, that coordinate of the surface, follows a radial geodesic on its way down. Just following radial geodesic. So we can solve for that as follows. So R is equal to 1/2 R naught, the original radius, 1 minus cosine of eta, which I'll define in a second, and tau, the proper time of the surface, is going to follow. Oh, shucks, I just skipped a whole bunch of. I'm like, I haven't defined that yet. Just a second. Skipped a little bit. One important thing that we're going to need in order to solve for the evolution of the surface is that at the surface, so interior, where there is mass, the metric is this closed Friedman, constant density, right? What is the exterior metric? Sure. So at surface, interior metric must match onto Schwartz metric. So there, we've got to agree with ds squared is equal to -1 minus 2m over rs, our short shield radius, dt squared, not tau, plus 1 minus 2m over rs inverse drs squared plus rs squared d omega squared. So that's our short shield metric. And it must be equal to this metric at the surface of the star. Right? It's like our boundary condition. So matching those two things together leads to some constraints on our coordinates. So what that basically means is that the short shield radius must be equal to r, the stellar surface, as a function of tau. And at tau equals 0, well, you'll see. So that gives us a constraint there. So now, since the surface must follow a radial geodesic, now we can write down something using our short shield metric and this constraint on our coordinates. So surface follows geodesic. And that gives us, for our radius, as a function of time, proper time, 1/2 r naught, 1 minus cosine eta. The proper time goes like r naught cubed over 8m to the 1/2 times eta plus sine eta. And matching those interior and exterior solutions gives me the following. I get a sub m is equal to r naught cubed over 2m, all of the 1/2. And sine of chi naught is equal to 2m over r naught to the 1/2, where this chi naught is the initial chi, right? It's the initial Lagrangian coordinate of the surface of the star. Okay? This immediately gives me some bounds on chi naught. Can you intuit what they are? If you're following along closely enough. Kind of comes from that sine function. 0 less than chi naught less than pi over 2. Just varying that, right? Unless we have like a bouncing universe. It just keeps going. Go back to cosmology, right?
Sean, when you say matching interior and exterior, does that mean only continuity or also smoothness?
Only the continuity of the metric.
Okay, so the derivatives.
That's right.
Don't match.
No. To get this, I didn't write out all the steps, it's true, but to get this, all you have to do is match the metrics, not their derivatives.
What is eta?
Have I defined that yet?
It's like completely blank. Oh, or.
What am I doing? I'm jumping all over the place. I'm so sorry. How did I? I'm not paying attention. Okay, we can fix this. Okay.
And AM is just the value of A at the surface.
Yes, hold on just a second. I'm just wondering, how did I skip a whole half page of my notes? I'm just going. I mean, this is loaded up in my main memory, but all right. So let's step back for a second. We're going to call this the scale factor. A is related to tau. Via a conformal factor, eta. Sorry, now we'll define it. And that's going to be this. So the scale factor is 1/2 AM, which is going to be a constant that we'll solve for. 1 plus cosine eta. And tau is equal to 1/2 AM eta plus sine eta. Right. And 0 less than eta less than pi. Like that. Those are our definitions that we're going to work with for the scale factor and tau in the Friedmann metric that we're using in the interior. And so now, with this, matching this metric to the Friedmann metric gives you this. Should have just forced myself to write out the steps. Okay. So this is a conformal factor. That's interesting right here. Okay. So now, let's figure out some equations of motion for our shells. This sort of gives us constraints on our initial conditions for these factors that enter into the equations. So let's start with the forward velocity. So the forward velocity UA is defined as the unit vector in the proper time direction, right? We've had that definition before. And it must satisfy the geodesic equation, or equations. Because we're in free fall. And so in that case, we get the following. I'll start holding my finger where I'm at in my notes so I don't skip ahead. UB grad sub B UA is equal to d squared xa, the coordinates, over d lambda squared, where lambda is an affine parameter, plus connection coefficient, ABC, times dxv d lambda dxc d lambda. That's just the geodesic equation, right? And now the rest mass density, which incidentally is also equal to the total mass density, the total mass energy density. Why? Why are the rest mass density and the total mass energy density equivalent? Pressureless. It's cold. There ain't no energy but mass. Yep. Okay, so in this case, the density goes like co-moving volume. Right, I erased my picture, but it's just collapsing. And so as the volume decreases, density goes up. And so just simply writing a very simple expression, the rest mass density is a function of tau relative to the initial rest mass density must go like some factor Q that's like a scale factor, must depend on the scale of the system, to the -3 as a function of tau. And this Q of tau is going to be equal to the scale factor divided by AM, which is 1/2 all times 1 plus cosine eta. It's from our expressions over there. Okay. And this also implies that the star remains constant density throughout the collapse, because it does not depend on the spatial coordinate, right? This is related to tau, not chi. So there's no dependence on the Lagrangian mass coordinate here, okay? And so throughout the entire star, it's the same density. Okay. On to collapsing it. Okay. So collapse is complete when the radius of our surface is equal to 1/2 R naught times 1 plus cosine of eta is equal to 0. When the surface reaches 0, that's when collapse is complete, okay? Which implies that eta of complete collapse is equal to pi. That's just our coordinate, right? We already established that the limits on eta were 0 to pi, but this tells you why, right? Okay, the proper time at collapse then is tau collapse is equal to R naught cubed over 8m all to the 1/2 times, we stick in the equation which is right here, right? So I've substituted for am, which we solved for already, stick in pi, so pi plus sine pi, right? That's 0. And so this is just pi times that. And so that's how long it takes the surface to collapse, and measured by proper time of the surface. Okay? So when this happens, you can look right here, right? So what happens here if I stick in pi for this cosine? Is 0. So Q is 0. What happens when I put that in here? Density is infinite. Singularity. Hey, we made a black hole. Cool beans. Right? So once that happens, a singularity forms at the center. And it's enshrouded by an event horizon. Okay? Right. And so we can actually compute the singularity forms first at the center of this collapse. And that's also where the event horizon forms first. And then the event horizon moves out in Lagrangian and radial coordinate until some limit. And we can solve for that. So I think now I'll draw a picture of what's going on here. And then we'll start from there. Okay, so looks like this. This is going to be R short shield over M, like that. And then this is going to be tau over M, right? Just normalized to the mass of the system. Obviously at 0, 0. And some of these numbers will actually matter. 1, 2, 3, 4, I didn't make this big enough. 5, 6. All right. And then 5, 10, 15, 20. So now let's think about that surface. So I picked some numbers here. And once you pick some numbers, you can actually solve for this. So let's say that the surface now starts out right here at RS over M of 5. In that case, you can plug and chug in these coordinates, dividing by mass as you go, and tau collapse is somewhere in the neighborhood of 12 or 13 in those units, okay? So that means that's the time that the surface gets to 0. So it goes like this, something like that. That's the time that every mass shell gets to 0. If you think about it, in order to have infinite density, you've got to have all the mass at the same place at the same time, right? And so every mass shell then reaches 0 at that same proper time. Like that. Okay? With varying amounts of in false speeds. Okay. So then, this being the surface falling in, taking roughly that amount of proper time to collapse, an event horizon actually forms before the collapse is complete. So you don't have to have a singularity to have an event horizon. That's not the definition of an event horizon. Event horizon is a region of space from which null geodesics cannot escape. Right? Outgoing null geodesics do not reach infinity. And so the event horizon forms before the singularity. It forms actually around 7-ish in these coordinates in terms of time, and it moves out. What is the final radial extent of the event horizon in these units? Why?
The short shield metric.
Yes, it's the short shield radius, right? It's just 2. It's just 2. So it ends up here, and it actually reaches here, right? At the same time that the surface is crossing that radius, right? So if you think about it, just logically, the event horizon reaches its maximum extent when finally all the mass is inside the event horizon. And so that's when it actually hits surface, and then it stays constant. And then you just got that, right? So the event horizon doesn't care what's going on in here. The formation of the singularity at the center doesn't affect the event horizon, right? Because it can't know anything about the singularity from a GR perspective, because all null geodesics originating from this event horizon ingoing can't come back. They all converge towards the center of the singularity. And so it's no different to the event horizon from this point, whenever, to the point that the singularity actually forms. Like that. Okay, and so, you know, from here on, we have a singularity at the center. That's that. And that is that. Okay. So that's the space-time diagram for what's going on in this collapse. All right, let's write down some stuff a little more rigorously then. Okay, so if we wanted to find this event horizon and actually compute the trajectory of the event horizon, this is what we do, okay? So the EH, which I'm just gonna abbreviate it, found by locating where outgoing null rays so, you know, light, satisfy, well, in the interior, right? In the interior metric. This is important. Satisfy ds squared equals 0. Sort of definition of being null. Okay. Plugging that into our interior Friedman metric, which at this point I've erased, so you'll just have to trust me. This leads to d tau, the proper time, is a of tau times d chi, our Lagrangian mass coordinate. Okay. All right. So using this, and did I erase it? One of the relationships between eta, I have erased it. But from the above equations, you can compute the following, which is d tau d eta. So just go back to your notes wherever I wrote down the expression for tau. I mean, it's this one, so I can remember what it was. Here it would be eta plus sine eta, right? And so I'm just going to take d tau d eta. That just gives me 1/2 am 1 plus cosine eta, right? And this must be equal to a of tau for our event horizon, okay? Great. So just looking at this and comparing to this equation here, I bring my d eta over to here, stick it right there. All of a sudden, that tells me that d eta and d chi are the same thing, right? Therefore, d chi is equal to d eta. Cool. All right. Even I can integrate this equation. Okay. So integrating, we get the following, which is chi is equal to chi of whenever the light ray was emitted, chi naught. Doesn't matter. But I'm not calling it chi naught because I don't want to confuse you with the surface. This is when the null ray was emitted, and from where the null ray was emitted, plus eta plus eta emitted. Can I integrate? Shouldn't this be a minus? That must just be a mistake in my notes. Okay. We know that the final radius for a Schwarzschild metric is 2m, right? We know that. So we can use that as a boundary condition. So in this case, the event horizon is that trajectory along which null rays that start at the center and hit the surface when that surface reaches r equals 2m. It's this, right? That's exactly what I'm saying. This is an outgoing null ray that starts at 0, and it just gets to 2m right when the surface gets to 2m. So by definition, that's what it is. And so I can turn that around and then use that, okay? So now, solving for eta, which is our sort of parameterized time unit in this case, r is equal to 1/2 r naught all times 1 plus cosine of eta, and I'm going to set that equal to 2m. So, right, and then I can solve for the eta at which that happens. And then I go back in time and say, how long would it take a null ray to, it's basically reversing the time direction. and saying go back in time to when that null ray was emitted. Okay? This leads to eta is equal to, I'm going to define this now as eta AH for apparent horizon, which is equal to 2 times inverse cosine of 2m over r naught all to the 1/2. Okay? Solving and using a trig identity, right? Okay, so now putting this into our trajectory, this equation, I can solve for the chi. Okay. Solving into trajectory of the event horizon. That gives us chi is equal to chi naught plus eta minus eta AH. Because we're pretending that this is, when was that null ray emitted, right? That's how our trajectory works. We're going backward in time to find this initial moment when that null ray was emitted that just gets to 2m, just at the same time that the surface gets to 2m. Okay. And then for all eta greater than equal to eta AH, which is equivalent to tau greater than tau of eta AH, the entire star is inside the event horizon. And like we were talking about before, the event horizon forms before the singularity. And this actually leads to, just put that up, singularity that forms is always inside the event horizon. This and some other evidence led to the famous Penrose cosmic censorship conjecture. Does anyone know what the bumper sticker version of that is? Yes, right. Nature abhors a naked singularity. There is no such thing as a naked singularity. And the caveat to that is from well-posed initial conditions. So you can design space-times that have singularities, but no event horizon. You can do it, but you can't come up with a physical scenario, right, in like this universe that leads to a naked singularity.
Sure.
For instance,
Make one.
you'd have to make one. White holes as well, right? And there are some wormhole spacetimes. Yeah. So you can do it. But they usually require probably unphysical conditions in some way or another. Okay. So once you have this event horizon, any rays, any null rays that are emitted interior to it will converge at the singularity. Any emitted outside of it will be able to escape to infinity. Any rays emitted right at the event horizon stay there, almost like they're trapped along that event horizon, right? And you see this, who's seen Interstellar? Who's hung out with Kip Thorne while he was making that? That was a hoot. Yeah, we had a long conversation at his house about it. So the image of the black hole, right? Like the event horizon is very bright because the light rays get trapped near the event horizon. Interior to it, they fall eventually into the singularity. Exterior to it, they can escape eventually to null infinity. But it's like an attractor for null rays an event horizon is. Okay. Now the tricky thing about the event horizon, which is implicit in all the analysis that we just did for Oppenheimer-Schneider collapse, is that you need knowledge of the global spacetime to locate the event horizon, right? This required us integrating the entire global space-time trajectories of various null rays to get where this event horizon was, as well as the surface of the star. It was a global property of the space-time. That can be pretty tricky, actually, to do in a numerical calculation and in a general configuration. What is easier to find is the apparent horizon. And we'll talk about that a little bit for the rest of class today. Finding the apparent horizon requires only local information about the space-time. So that's a lot easier. Yeah, thanks, Steve. Okay. So let's go ahead and talk about locating event horizons. Got this figure, right? Questions about Oppenheimer-Schneider collapse? Hopefully it is. I mean, I can give you a bunch of references that actually use this as a test problem so that you can see the nuts and bolts of how it actually gets applied. But this is an analytic solution that you can test your numerical DR code with. So let's talk about locating the EH in a numerical simulation in a little bit more detail. There in the Oppenheimer-Schneider collapse case, it was fairly straightforward, right? It's an analytic solution. Okay. And in general, we're going to need to wait until the space-time settles down to a quasi-steady state in order to avoid rapid changes in the space-time. Hi. Oh, yeah. Oh, sure. No worries. I'll stick it. Thank you very much. I thought someone was just trying to sneak a peek at the lecture.
Big enough room.
Why is that person staring at me? Okay, so once the space-time has settled, we can start to look for the event horizon. So you don't want to be dealing with any event initial transients or things like that in the numerical solution. And what you can do is you can evolve null geodesics to locate the event horizon, right? That's what we did just now with the Oppenheimer-Schneider collapse, right? We evolved a null geodesic from the center to see when it intersected 2M at the same time that the surface intersected 2M, right? And so in the same, I don't have it up on the board anymore, but you would use the geodesic equation to do this, right? D lambda squared is equal to the Christoffel symbols associated with the 4 metric, dxb, d lambda, dxc, d lambda equal to 0. You'd evolve that. You'd select a bunch of them and try to find the ones that can't escape to infinity. Okay, so using the definition of 4 momentum, 4p is what I just wrote on the board. You would have understood what I meant. And splitting into 3 plus 1. So we're going to take our original 4D metric and split it into 3 plus 1 with the ADM metric in general. We can get the following. Okay. So here's my momentum. the spatial components of the momentum, which by definition are the derivatives of the coordinates with respect to the affine parameter that we're differentiating along the trajectory, basically, that I'm caring about. And then the time component of the momentum is our spatial metric, gamma ij, pi, pj, the 1/2 all over the laps. That's just from the definition we had a long time ago for the 4 metric in 3+1. And recall that, and I've used this in writing this down, GAB, PA, PB is equal to 0, just by construction of the definition of the 4 momentum. Okay? So then, plugging this in and splitting, so I'm going to plug this in to our geodesic equation. I'm going to split this second order differential equation into 2 first order differential equations. We've done this before. I don't know if you remember, but we've done this before with the geodesic equation. Might have been all the way back when we were still in Thorne and Blandford, but we have done this before where we've split this into 2 first order equations. All right, that's going to give me a first order equation for the momentum, dpi d lambda, is equal to minus the laps, partial with respect to I of the laps, all times the time component of the momentum squared, plus partial with respect to I of the shift vector beta k, p sub k, times p upstairs 0, the time component, minus 1/2 partial with respect to I of gamma ln, the spatial metric, p downstairs l, p downstairs m. That's one of them. And then my second equation, dxi d lambda, telling me how my spatial coordinates connect to my affine parameter, the trajectory, is gamma ij, p downstairs j, minus beta, the shift vector upstairs I, and the time component of the 4 momentum, like that. Okay, so now these are first order ODEs. I can solve these. And the method that you would use is to select some events, XA, and integrate from there in random directions, PIs, right? And find the ones that can't escape, okay? This is a numerical procedure, right? So what you start with is for some XA, integrate in many directions, which I'll just call PI. And then if you find that the ray that you're integrating along escapes to infinity, it's not inside the event horizon. If the ray does not escape and instead converges towards 0, it's inside the event horizon. Now, I mean, that's sort of a brute force approach, right? That's sort of a brute force approach, but that's one way to do it. It's actually easier in practice to integrate backwards in time rather than forwards in time, to find, instead of where are the null geodesics diverging from, find where null geodesics converge to. Because remember what I said about an event horizon, it's an attractor for null geodesics. And so practically speaking, the procedure is the same, you just flip the sign of time, and you integrate backwards to see where are the null geodesics converging to. And then that gives you a location for the event horizon. Okay. Question? That's a brute force way of doing it. But we'd like a more elegant way of doing it, or at least one that's a little more practically feasible. So rather than doing this, and this involves integrating individual rays, right? For each event XA, that's an individual ray that I'm integrating. And so it could involve a lot of integration of individual rays. Instead of doing that, you can construct a 2+1 null hypersurface in your space-time. and try to understand the properties of that, okay? So what we're gonna do instead, construct 2+1 hypersurface. Okay? Oh, I'm sorry. Null hypersurface. That's an important aspect of this hypersurface. We're going to define this as the level function or the level surface. Level surface. Talked about level surface when we were doing the differential geometry stuff. Of some function. I have some choice in this, and I'll make motivated choices. And that function is going to be some f of time and space coordinate xi, and I'm going to set it equal to 0. And I can choose that. Setting it equal to 0 is the easiest thing to do, but you can set it equal to something else. And so I'm just going to define this. I haven't said anything about a connection to horizons or anything, but I'm going to use this as a mathematical framework to try to locate where the event horizon is. And the fact that it's a null hypersurface is going to help me do that. All right, so the normal vector to the surface, which is hypersurface, is the usual thing, right? We had this before too. It's just the partial sub A of that function f, because that function f is the level surface of my 2+1 hypersurface. And so the normal to that is just the partial derivative, right, of that level surface function. And this must also be null. Cool. And from the definition of the metric, GAB times the partial of f, partial b of f has got to be equal to 0, right? For it to also be null. Great. Okay, so now let's solve for the evolution of this function. We want the time evolution of this function. And I'm going to use this equation to do it, along with just my general definition for f. All right, so it's basically working this out. You end up with a quadratic equation, which you can just use the quadratic formula to find your solution. And I'm going to select the positive of those solutions, just as a choice, okay? So now solving for the evolution equation of this function. I get, when I select that positive root, partial with respect to time f is equal to minus g upstairs ti, so the time component and then the spatial components of the metric, the 4 metric, partial with respect to I of f, plus, here's where I selected the positive rather than the negative, square root of g upstairs ti, partial with respect to I of f, all that squared. I'm going to run out of room here. Minus g upstairs time, g I j, spatial components of the 4 metric, partial with respect to I of f, partial with respect to j of f, all that. Oh, yeah. Like that. And then all of this divided by the time component of the metric. So that's just an evolution equation that comes from this, is all. Working that out. Okay? Substituting in the ADM metric and re-expressing this in terms of my spatial quantities, lapse and shift. What I get is partial with respect to time of f is equal to the shift vector beta I, partial I of f, minus the lapse times the spatial metric, partial with respect to I of f, partial with respect to j of f, all that to the 1/2. Simpler and easy to work with. Finding solutions to this is easy in spherical symmetry, it turns out. Okay? So let's do that. So the solution to this equation is pretty easy in spherical symmetry. And so, in spherical symmetry, f is a constant along outgoing rays. So we can use that to turn this around, right? And furthermore, another useful thing, which we didn't cover, but is in the book, in Kerr-Shield coordinates, light rays like that, outgoing light rays, follow characteristics. And there's a solution for that in Kerr-Shield coordinates. So we'll use that. And that is the following. T minus R is equal to 4 times m natural log of the absolute value of R over 2m minus 1 absolute value plus some constant of integration. Like that. Okay? Now, using that, so outgoing light rays must obey this. F is a constant along such outgoing light rays, and so this has got to be 0. So using this into here, I can deduce that F, my function, which satisfies my constraint on my null hypersurface here, must essentially be this. F must be a function of that, right? T minus R minus 4m natural log of the absolute value of R over 2m minus 1 absolute value. I can drop the constant because it's just a function of this thing. Who cares about the constant? Okay? So this must be a solution to my geodesic, or I'm sorry, the evolution equation for this level surface. Okay. And solving that, I can find the event horizon, which will, of course, be analogous, synonymous with this level surface. It's still not as easy as we'd like. Easier is apparent surfaces. The book goes into a lot more detail on this stuff. And so if you were to actually do this, go and look there. But this is the general gist. It's fairly high level overview, I think. Doesn't really get into much of the guts and gory detail. We don't have time for that. Questions though? And I haven't looked at the relativistic hydro book. Do they talk at all about finding event horizons?
Towards the end of the book, they might, in the last section where it's applications, the first 2 parts of the book don't.
Yeah, they get less into the relativity stuff. Okay, so apparent horizons. Last little thing today. These are easier to find than the full event horizon because they depend only on local stuff, which hopefully we have time for me to show you. And they're always interior to the event horizon. That's another useful feature of them. So if you find the apparent horizon, you know that must be inside the event horizon. So you bounded where the event horizon has got to be. Okay? So let's do this procedure. We're going to let big S be a spatial hypersurface. To surface, which is embedded in our manifold sigma, our 4D manifold sigma. And in this, little s vector A is the outward normal to S. And that is also living in the manifold sigma. And it's purely spatial. And for that, we can choose, since it's a norm, right? It's a normal, right? There you go. And since it's purely spatial, if I dot this into the unit vector, this is 0. The normal vector, right? Because the normal vector points in the time direction. S is purely spatial. Okay. Okay, so now I've got this 2 surface. And just like when I embedded a 3 surface into sigma, the 4 metric induced a 3 metric, which we call a spatial metric. If I embed a 2 surface into the 3-dimensional space, the 3 metric induces a 2 metric on that surface. This is differential geometry, right? Okay, and so from gamma AB, we get a 2 metric, which is MAB is equal to gamma AB minus SA SB. That looks a lot like our definition for the spatial metric, the 3 metric, right? All right. And that is just substituting in my definition for gamma, GAB plus NA NB plus SA SB. Sorry, minus there. Okay. So let's find the tangents to 2 future pointing null geodesics. Doesn't matter what they were, what they are. So the tangents to 2 future pointing, so we're moving forward in time, null geodesics. We're going to use these to try to give us some idea of how null geodesics are evolving on this 2 surface. So that's why I need 2 of them. We're going to define them. Ka, which I'm going to define as 1 over the square root of 2, all times n upstairs a plus sa. I'm going to call this one the outgoing. These definitions of outgoing and ingoing are somewhat arbitrary and confusing, but this is what's used. And then LA is similarly defined as 1 over square root of 2 NA minus SA. And this is, we're going to call this the ingoing tangent to a null geodesic, or tangent to an ingoing null geodesic. Okay? Now, with these 2 definitions, I've got some relationships between them. So Ka is equal to 0. MAB times Ka is similarly equal to 0. LA is equal to 0. MAB LA is equal to 0. And then KAL upstairs A, so the dot oops, I switched them. I don't think that matters. That actually might flip the sign. K contravariant L covariant is equal to -1. So now let's solve for the 2 metric in terms of these tangents to my null vectors, to my null geodesics. All right? Solving for the 2 metric, we get MAB is equal to GAB plus KALA plus LA KA. Pretty easy. Pretty easy. And that's just using this and rearranging, right? Using these to replace these. Yep.
For the K, it should be KALB.
Yeah, absolutely. In fact, did I say that out loud and I wrote A's there? Did I say A's? Jeez. Must be getting close to the hour. Yeah. Okay. Yes, thank you, Mike. Okay. So what we're going to do with these 2 tangents to 2 different null geodesics is we're going to measure their divergence or convergence, right? Because remember, event horizon is an attractor. Things converge there. At least back in time, right? So that's what we're going to use these 2 different tangent vectors to do, is measure this expansion, okay? So the expansion of outgoing null geodesics that are orthogonal to my surface. Big S. That's an important aspect of these 2 tangent vectors. We're talking about null geodesics that are orthogonal to that surface, right? Moving away from it. Maybe a picture is worth 1,000 words, which I did not draw, but it kind of makes obvious, intuitive sense, right? I've got here's a projection of my 2 surface, right? It's a circle. And I've got geodesics which are orthogonal to it. And I select 2 of them. I want to measure the expansion as we propagate forward in time of those 2 null geodesics. Are they converging or diverging, right? I'm measuring properties of the curvature of this surface and how curved it is. And if it's curved enough that I can't escape it if I'm a null geodesic, is where we're ultimately going with this. Okay. All right. So now, that expansion of these null geodesics, I'm going to call capital theta, which I always think looks like a football. And that's going to be MAB grad A K B. Okay. What's going to be called the outer trapped surface, or any outer trapped surface, not the, but any outer trapped surface has capital theta less than 0. So these null rays converge, right? Negative expansion, they're converging. And so it's a surface that is trapped. Null geodesics originating from that surface converge rather than diverge. Okay? The boundary between these trapped surfaces, or the outer boundary of the outermost outer trapped boundary or surface is the apparent horizon. And in this formalism, this is now something we can solve for because that's where capital theta equals 0. So where is the expansion of null geodesics originating from surface? 0. They stay together. They don't diverge or converge. That's the event horizon below. And this, actually, it's the apparent horizon. In some spacetimes, it's the same thing, but not here. So we can use this then to solve for apparent horizons. All right. So let's assume spherical symmetry for a second. Good old spherical cows, very useful. And let's pretend that our line element takes the following form, which I'm going to add some factors in there which do not change the generality of this line element whatsoever. But you'll see where we're going with this. So our line element is going to be this. It's going to look like the normal ADM, but with some extra factors. Capital A squared, beta squared. And I'll explain why that doesn't have, why that's not a vector in a second. dt squared plus 2 times a squared beta dr dt plus a squared dr squared plus b squared r squared all times d theta squared plus sine squared d theta d phi squared. Sine squared of theta d phi squared, of course. Right. So now in spherical symmetry, the only element of the shift vector that's not equal to 0 is the radial shift. And so I'm just going to call that scalar beta, because all the other components are 0. And so that's what I've done here by dropping in the indices on my shift vector. This is now just a scalar, which is just the radial component of the shift. Okay? And this implies that the lapse, the shift, and these two coefficients, A and B, are functions only of time and radius, R, in this metric. Spherical symmetry, right? That's what we've done. Okay, so now let's take our surface. Let's put a surface in this spherical geometry, centered on the origin. All right? Get to use my drawing again. So many uses for a circle. So we've got a surface, a 2 surface, centered on origin. Okay? In those cases, I can take the spatial norm, this SA vector, which we've been working with, and I can deduce the components of that is 0 in the time slot, 1 over A in the radial slot, and 0, 0. That's my norm to that surface, right? It's kind of obvious. All right, and this is the spatial norm. Lowering the index on that using my MAB metric, I get S covariant is alpha, beta, A, 0, 0. That's just using MAB.
So alpha, beta, the root, A, beta.
I meant A beta. Capital alpha, obviously. All right. So then an outgoing null norm. Sorry, picture. So beautiful. Okay. So that comes back to our the tangents that we were working with before. So this is the outgoing one that I wanted to work with. It is 1 over square root of 2 all times A beta minus alpha A 0, 0. Those are the components of it. Again, this is all just plugging through the equations that we had. Raising an index on that using MAB is going to be 1 over square root of 2 inverse of the laps times 1 over a minus alpha to the minus 1 times beta, the shift, and then 0, 0 in the angular components. And then from this, I'd really rather write this over here, but I don't think I have space. We'll just do it here. Okay. And then the 2 metric is diagonal, and it is 0, 0, b squared r squared, b squared r squared, sine squared theta. Okay, so now let's plug into the expansion. So capital theta is m ab upstairs, grad a kb. And working this out, which I don't do in the notes, this is all equal to, when you plug these things in for here, you use this, raise the indices, you can get the following. Square root of 2 over rb, all times 1 over alpha, partial derivative in time of b times r, plus quantity of 1 over a, minus beta over alpha, partial in r of br, closed. Like that. This is not particularly enlightening, right? But it turns out that this is related to the rate of change of the areal radius. Remember when we talked about the areal radius related to black holes? Those are essentially that radius that gives you the area of the surface of the black hole. Okay? And so that actually makes this somewhat useful. So proportional to rate of change of the areal radius of a black hole, which we're going to call R area, happens to be equal to B times little r in these coordinates. Okay? Now, combining all that together, therefore, I can derive the following. K upstairs A, grad with respect to A of the areal radius is equal to K upstairs time, partial in time, of the areal radius, BR, plus K upstairs R, partial R, BR. Like that. And this is equal to 1 over square root of 2, just substituting in now. 1 over alpha, partial in time of BR, plus 1 over A minus beta over alpha, all times partial in R of BR, just like I had before. Okay? Just like that. Combining these expressions, I can then solve for this. So capital theta is equal to 2 over the areal radius times K upstairs A, grad A of the areal radius, which is equal to 1 over 4 pi areal radius squared, Ka grad A of 4 pi areal radius squared. And what this implies is that this capital theta measures the fractional change in the area of some emitted pulse of light, or some spherical flash of light. So if I were to, set off a little strobe light at some event, XA, in my space-time, what this is telling me is that this will measure the change in the area of that spherical pulse of light. So if that spherical pulse of light gets smaller, it's inside the apparent horizon, and it's collapsing towards the singularity. If the spherical pulse of light gets bigger, it's outside the apparent horizon, and it can escape to null infinity. All right, I know that was very fast and terse. So if we need to find event horizons or apparent horizons, we'll have a little bit more work to do. But these are the general approaches. We didn't even get into any of the details. In the book will generalize this to specific coordinate systems, including spherical and Cartesian, in a more general way than I have time to do in class. But question, Eric?
About OS collapse.
Mm-hmm.
Will we have to apply this? Or we won't have to apply this?
You won't have to, unless you really wanted to do it as a metric for your validation of your code. You don't have to find the event horizon.
Okay.
But if you want to do it and make sure that it matches the analytic solution, which is a good thing, then yes, you will have to come up with some way of numerically finding the event horizon from your calculation. Finding the apparent horizon would be easier, but since the OS collapses spherical symmetry, you could probably, in a fairly straightforward way, actually solve for the event horizon numerically. Yeah. Most of the time, we just make sure that it collapses in the correct amount of time, and then assume that everything worked itself out. Other questions? Okay. That's all. For Monday,